Hello, Chem 2. Welcome again to our weekly videos. We're about ready to start a new chapter. Chapter 11 is called Rates of Reaction or Chemical Kinetics is what I have it labeled as in your OneNote. So, what are we? We got going to be the same thing as last time. You guys should still have the Chapter 8 exam on your hands to complete. Do that as quickly as possible. But just like the other ones, there is an optional OWL mastery questions, and there's required OWL problems for chapter 11 already available, should have been available as of Monday morning. So the chapter, this was a big one. It actually goes pretty long. We're probably going to spend 2, maybe 3 weeks doing this. But we're going to talk about the meaning of reaction rate today. And then tomorrow's video will be all about reaction rate and concentration. That's a biggie. And we'll focus on that one tomorrow. But today we're just going to deal with the meaning of the reaction rate. So key concepts in this chapter, I'm going to talk about what is the rate of expression, how do we figure it out from initial rate data, from concentration time data, from reaction mechanisms. We're also going to relate how the concentration versus time is in a first order reaction. And then we're going to use what's called the Arrhenius equation. This is a chapter that if we were in school, we'd have done this really cool lab that does a really good job of showcasing how this works. And I'm going to cross my fingers I can find some video along the lines so I can share with you. But this actually was a lab that usually is very, very impactful to explain a lot about what's going on here. But we're going to try to do our best without that video. Okay, so first section is section 1. It's just the meaning of reaction rate. What does it mean, the rate of a reaction? So as you might be well aware, and it might be kind of commonplace, when you talk about rate, you're talking about speed. But speed usually has this sense, this idea of some motion, this going from point A to point B over some instance of time. Well, the difference here is we're going to be looking at how a reaction occurs over time. So we're going to look at what happens to the amount of reactants or the amount of products and how those amounts change over time. Now, some things to know, and if you watch the videos that I provided on OneNote, they do a really, really good job of trying to explain some really quirky ways about how reaction rates can be impacted. You can change the rate of reaction using concentration of the reactants. The higher the concentration of the reactants, the faster the reaction is going to go. You can change the rate of the reactions by changing the actual process at which the reaction takes place. Might talk about adding a catalyst, or might talk about the pressure or something like that, but change the process that's the reaction is going to take place. Change the temperature. I think we're all pretty aware that things that are warmer tend to react faster, and hopefully by the end of this chapter you'll understand why that is. There's a reason why you put things in a refrigerator to keep them from getting funky. Is because that reaction is going to take place regardless. Anybody who's ever put milk into the refrigerator and had it go bad, you realize it is going to curdle, it is going to go bad, but in the refrigerator it's going to take quite a bit quite a bit more time to occur because it's a much slower reaction. You leave that same milk on the counter, it's going to get funky real fast. Presence of a catalyst. You should know what a catalyst is from biology. Talking about a catalyst is something that speeds up a reaction without itself being impacted by during the reaction. And finally, what the mechanism is. What are the series of steps that take place? How does the reaction take place? How do you go from reactants to products? That's going to change the speed of the reaction. So we're going to focus on all these, but early on we're going to focus a lot on concentration. So when determining the rate of the reaction, we're going to look at a mathematical expression that allows us to compare how the amounts of the reactants and the products change over time. So for instance, in this reaction is given here, N2O5 is going to decompose into NO2 and oxygen. But you notice the coefficients. While this reaction occurs, N2O5 is going to go away. But for every 1 mole of N2O5 that is decomposed, you're going to make 2 moles of NO2 and 1/2 of a mole of oxygen. What that means is the rate at which the change of N2O5 occurs is going to be half of that NO2. So if I want to make them equal, I'm going to take NO2's rate, the amount of change that happens over time, and divide it by 2 to make them equal. Also, on that same regard, N2O5's rate of decomposition is going to be twice that of oxygen, because oxygen is going to be created at 1/2 the rate that N2O5 decomposes. So you would have to divide by the coefficient. Notice for each one of these, you get this interesting dynamic where you've got the change in concentration divided by the coefficient that is in the balanced chemical equation. Now, the other thing I want you to notice is this over here has a negative sign on it with the N2O5, and the NO2 and the O2 have a positive sign. Well, that is because N2O5 is going to go away, is going to be exhausted, is going to be decomposed, while NO2 and O2 are both going to be created. So the rate, the speed at which one goes away is going to be compared to the rate the other one occurs. So a way to talk about the rate is divide by the time. So if you're talking about how much goes away over time, if you divide by time, you're going to get a speed or a rate the reaction takes place. And again, notice it's concentration divided by time, concentration divided by time, concentration divided by time. But the big differences are each one of these concentrations are going to be divided by the coefficient that's directly in the balanced chemical equation. Now, notice this is that same reaction we just had. So suppose you started with 0.16 molar of the N2O5 and none of the other two. Well, notice as this reaction is taking place, going like in 2 minutes, you've cut the amount of N2O5 in half. It's gone from 0.16 to 0.08. But at the same time, NO2 is increasing by a factor of 2. So as you decrease this by 0.08, the amount of NO2 is going to be 0.16 or twice as much, while O2 is going to only increase by 0.04 or half as much. So you have this difference. The products are going to increase in concentration over time, and your reactants are going to decrease. Another thing interesting to notice here is in the beginning, those rates of change are really, really fast. But towards the end, the change doesn't happen very quickly. Well, that's because there's not much of that reactant available in the end. We already said one of the ways to change the rate of a reaction is to change the concentration. As the concentration of the reactant decreases, your rate of change is going to also decrease. So, general formation. If I have, and you're going to see this a lot for this chapter and next, where you're going to have these generic reaction expressions, where it's A plus B giving you C plus D, and they're going to give you each one of them with a coefficient out front. Whatever the coefficient is, once you balance the equation, goes there. The rate of the reaction is going to be, well, for both reactants, it's going to be a negative, and for both products, it's going to be a positive. So if I want to figure out the rate of the reaction, I want to find out how quickly this goes away. So the concentration of A is going to change in a negative way. So you're going to take the negative of that to turn it into a positive value. You're going to divide it by two things. You're going to divide it by the coefficient for the balance equation, and you're going to divide it by the time. So rate is going to be the change in concentration of the reactant divided by the coefficient of the reactant divided by time. And you'll notice the same expression for all of them. So for instance, if you had ammonia's reaction is like this. If I wanted to figure out what the rate of the formation of ammonia is, or the rate of the reaction of creating ammonia, I'm going to either take my concentration, my change in concentration of nitrogen divided by time. I'm going to take the change of hydrogen divided by 3 and divided by time. Or I'm going to take the change in concentration of the ammonia and divide it by 2 in time. In all situations, I'm going to get the same value. In this case, for this temperature, that amount is going to be 0.1 moles per liter per minute. What that means is the ammonia is going to be made at a rate of 0.2 moles per liter per minute, while as the hydrogen is going to be exhausted at a rate of 0.3 moles per liter per minute. It's going to be varied based on the coefficients in the balanced chemical equation. So let's try an example. So we have this generic reaction. You notice the coefficients are 1, 3, 1, and 2. It says express the average rate of the reaction with respect to each of the products. Well, we've already seen this. You know there's going to be the change in concentration of each one of them divided by the coefficient. So the change in concentration of A divided by time, negative because it's a reactant. The change in concentration of B divided by time in 3, negative because that's a reactant. Change in concentration of C divided by time, change in concentration of D divided by 2 and divided by time. It's whatever coefficients go in the denominator. It's a change in concentration on top. Reactants get negatives, the products get positives. Okay, so let's use it. So for the first 20 seconds of the reaction, the concentration of B drops from 0.1 to 0.0357. What's the average rate of the reaction in the first 20 seconds? So first we got to figure out how much B drops in 20 seconds, divided by time, and then convert that over to the rate of the reaction. So we know we have the time. We now have the initial time. You're going to see this format here again with this unit and the next. We're going to put square brackets around a letter or a compound. That means concentration of. And this subscript right next to it tells you at time whatever. This happens to be at time 0 at the beginning. So this means what's the concentration of B in the beginning? It's 0.1. Concentration of B after 20 seconds is 0.035. We already said that the rate of the reaction is going to be, if we're expressing in terms of B, is going to be negative change in concentration of B divided by 3 and divided by time. So we're going to put all of our numbers in. We have the initial, we have the final. Remember, delta is always final minus initial. And we have the time. So we're going to plug those numbers in. So we have the average rate is going to be final 0.0357 minus 0.1, that's your change in concentration of B, divided by 3 and divided by 20 seconds. The rate of change is going to be 1.07 times 10 to the 8th third molarities per second. So you have molarities on top, seconds on the bottom. That's the rate of this reaction. Okay, second thing, or letter C, predict the change in concentration of D during those first 20 seconds. Now, change in concentration is going to be very, very different because now we're going to try to figure out what delta D is. Delta D is over the first 20 seconds. We already know what delta B was. Now we have to relate it to delta D. So we know from part A, the rate for the D, if with respect to D, is going to be negative change in D over 2 T. I think we're going to have to change that to a positive. That's a positive there. Sorry, that's my bad. We know the rate of reaction is 1.07. So change in concentration over 10 seconds. We're going to solve for delta D. So delta D is going to be, again, take the same rate law expression here, and we're going to just solve for delta D. So it's going to be rate times 2 times change in temperature. So rate is, get from the previous example, times 2 times 20 seconds. The concentration of D is going to increase by a factor of 0.0428 molar over those first 20 seconds. So the numbers are different. It says you realize that what we saw in C, the change in concentration of B and change in concentration of D are different. And that's because they have different coefficients. They have a different concentrations, different starting points, different ending points, but the coefficients are also very different. Okay, so how do we measure the rate? Well, if you watch the videos, they talk about a lot of different ways to measure the rate, but what you have to find is some way, shape, or form to see the reactant go away or to see the product being created. If the reactant or product happens to be a gas, you can change volumes. But one of the things that happens very, very frequently is you look at color changes. If the reaction occurs and a color either goes away or a color is created, then you'll use that color change to determine the rate of the reaction. One of the videos that I shared with you talked about Beer's law. Please watch over that. We're going to use that a couple times over here to explain what's going on. So we'll go back to that original reaction, N2O5 making NO2 and oxygen. Well, one of the things about this is that NO2 is a really, really brown red gas. So you're going to see a change in the intensity of that brownish color over time. So you're going to see this stuff, N2O5 is clear, but NO2 is brown. So as this reaction occurs, you're going to get more and more of an intensity of a brownish red color gas. And you can measure that using what's called a colorimeter, not a calorimeter like from the last one, but a colorimeter where you send light through it and you figure out how much light is absorbed by the color. Again, one of the videos that I share with you does a really good job of trying to explain that. I'll probably try to find for tomorrow another video that will help explain Beer's law a little bit better. But the idea is, if a color is going to go away, think in terms of like fading of your clothes. If you're going to talk about fading of your color in your clothes, over time, the color is going to fade. So if you can measure that intensity of, say you have that really, really red, bright red t-shirt, and you can measure the intensity of that bright, bright red t-shirt, and you can measure how intense that red is every single day, you would see a decrease in the intense red color over time. That is a way to measure the rate of the reaction. How fast does that t-shirt lose its color? This just happens to be something where it's making a color. It's making a reddish brown gas. So the change in pressure could also be done here, because you'll notice that in this reaction, you start with 1 mole of gas, but you end up with 2.5. So since there is an increase, if you can measure the pressure, the intense pressure in this reaction, you could see how much the pressure increases, and you could extrapolate and do some stoichiometric math to figure out what that is. But it's just another way to measure how fast the reaction takes place. There's a few ways to do that, but again, you have to have some physical way to see the reactant going away, or a physical way to see the product being created. This is an example where they take this blue dye that's in the beaker, and they dump some bleach into it. And you'll see that after 2.5 minutes, the stuff's faded, but after 5 minutes, it's even more faded. That makes sense. Over time, you're going to see this decreasing. That is the rate of the reaction. So if we can measure how intense that blue color is at 0 minutes, at 2.5 minutes, and at 5 minutes, we could get an idea of how fast the rate of the reaction occurs. And some other information, which we're going to extend about a lot more in the next two sections. Now, if we were to try to determine what's called the instantaneous rate, if we go back to that cool example that we had earlier about the N2O5 being decomposing, in the beginning I said that the rate of the reaction was kind of fast, and you saw that because the NO2 and the oxygen both increased kind of fast in the beginning and it tailed off. Well, one of the ideas, one of the concepts that occurs is what's called an instantaneous. In our example we used, they asked for the average rate of disappearance. Well, what if they want to know at any given moment in time, this situation is exactly at 2 minutes, what's the rate? Well, what you would want to do is find what's called a tangent line to the curve. Now you'll notice a black line on this is like set right up against the curve, flat up against the curve at 2 minutes. So that line represents the rate at which the concentration is changing at 2 minutes. So if you do your rise over run, you remember that good old stuff from slope math. Rise over run, the rise was it dropped 0.056 molarities, and it did that at the time that they used there to figure that out was at 2 minutes. Went from the 1 minute to the 3 minutes. So the rate at which it's changing at 2 minutes is 0.028 molarities per minute. And it is negative because it is decreasing. So if you need to know the instantaneous, you're going to have to know what the tangent line is at that point on the curve. Okay, so that talks a lot about the different ways that rate can be measured, what it means. What we'll do in tomorrow's video is we'll talk a lot more about how that works. So here's an example. Determine by calculating the slope of the tangent line versus the time of the curve desired. It's just going to be, the rate is going to be the negative of the slope. That kind of makes sense. Let's look at this. If this rate, and this is our coefficient, this is our rate, that N2O5 goes away, we know that from a previous example that the rate of the reaction was the negative of the rate at which A went away. So it's going to be the negative of the slope. So what's next? Tomorrow's video, what I'm going to do is we're going to talk a lot more about this concept of how the concentration of the reactants can change the rate of the reaction. A little bit of why, but a whole lot of math is to figure out how. I hope everybody is being safe, being healthy, and doing their best at social distancing. Now we have to add the get that mask, put that mask on when and if you go outside. Be safe, guys. I'd like to see you guys sometime after the 15th. So do your part, be healthy, be safe, and I'll see you on the next video. You thought I forgot. Always remember, never forget, sig figs really do matter. Toodles.